So now we move on to the real thing. What's a neutrino? I'm not the guy to tell you, and I don't know why you need vast amounts of still water in one of the deepest mine shafts on Earth in order to capture them. But apparently Tony Noble, our next speaker, Tony, is he on stage? Oh, here he is, okay. Has a taste for the pursuit of things that are really hard to find. One of his next projects is to pursue ideas for detecting dark matter. Tony.
Thanks very much. It's certainly an honor to be here. I must say, if there's some film rights going on Hominids, I want in on that, since Robert actually came to visit us in Sudbury to get things right for the story, and had a very nice visit with his wife underground. And it's really a nice book, and he really got things right in large degree as to what we have down there, with the exception about the parts of people jumping in the heavy water and this sort of thing. Yeah. Anyway, to put my talk in perspective, maybe I'll start with the first slide, if you don't mind. Yesterday we had a series of discussions on exploration, and we heard some wonderful talks about the exploration of inner space, where Jean-Michel and Phil talked about our exploration of the ocean, and I'm always amazed that, I can reach out there and I can put my foot in the ocean with no effort at all, and yet we still know so little, and we have explored so little of the ocean. It's quite remarkable. Then we heard from Dave and from Darlene about how we're pushing the envelope to get into space, into our own solar system, and let me go back on that. Get the right button here. So we're working out our way out into the solar system. We've been to the moon, of course, and now Darlene is talking about these courageous people who are going to go out and explore as far out as Mars. And I find these people are great and fantastic, and I'm really inspired, and yet at the same time very humbled. I look at where we are. I mean, here's our star, one of 400 billion stars in our galaxy. 2/3 of the way out to one of the spiral arms. Not very significant, not very special at all. And our galaxy, again, is not very special. One of more than 100 billion galaxies in what we know of the visible universe. So we are rather lonely and rather small down here. And we are doing the best we can to expand out of here and explore our solar system. But there's an awful lot out here that we really don't understand. There's an awful lot that we do understand through all the astronomy and so on that's going on. And what I want to talk to you about today is the use of neutrinos that we're studying in our lab, which actually tells us a little bit and contributes a little bit to the science of what's happening out here in our universe. Before I came here, I was sitting down with my parents, who very kindly drove all the way from New Brunswick to Kingston to look after our kids while my wife and I are here having a good time. And my father asked me what I would talk about, and I said, well, I'm going to explain about the neutrinos and Sudbury and what we learned and so on. And he listened very patiently, as he was wont to do. And afterwards he said, if you hadn't done this experiment, or would the world be worse off for that? And it's a very deep question, and I thought about that for a while and said, of course, this experiment has had impact. And I think that's been reinforced at this meeting. We've had so many people talk about their passions, and although I often feel that I'm in this little microcosm of astrophysics, and the people I talk to are generally at astrophysics conferences, very narrow view of the world. And yet I see, when I come to places like this, that the science is really part of our culture. There are people out here everywhere that are exploring science and other passions in their own way, and it's this kaleidoscope of people that has really made up this mosaic, which is our culture today. And so I think that what we're doing is important, and I'm going to try and tell you a little bit more about it. So Moses said, what is a neutrino? And of course, this doesn't show up very well. But anyway, the fundamental constituents of matter. Now, I'm not sure why it disappeared, but under ordinary matter, there used to be a picture on my screen they run a Mac, of a bottle of beer. So ordinary, maybe it's been censored because you can't show beer, I'm not sure. But ordinary matter was a bottle of beer. And I was going to point out that if you look closer, in fact, that's largely water. In fact, this is a recycled slide. I used that mainly for an American audience. And if you were able to look closer inside this molecule of water, of course, you would see that the atoms inside that molecule are made up of the neutrons and protons. And even 50 years ago, that's all we knew about. We thought of course, atom means something that cannot be divided. That's what we thought a long time ago. Then we came up with neutrons and protons, and we knew that was the fundamental particles. There was nothing else. And now, of course, we know that the neutrons and protons are made up of quarks, and of course, now we know those are the fundamental objects, and there's nothing else. So it's quite fascinating, but we've been able to build what's called the standard model of particle physics, which describes all this plethora of particles that we particle physicists are excited about, which are listed there on the right. But they're really made up of a basis set of not very many particles. There's the quarks, which combine to make all the things that we call matter today in various forms. And then there are the electron that everybody is familiar with and his partners, and then a bunch of neutrinos. And so these neutrinos are fundamental particles in our sort of basic set of particles that define everything that's in the universe. We still haven't really told you very much about neutrinos, and we don't actually know an awful lot. That's why we're researching them. They're a subatomic particle. They have almost zero mass, and in fact, for the last 30 or 40 years, we thought they did have zero mass, and it's only the results of our experiment and other experiments that have shown that that's not quite true. They're very abundant. To give you a feeling, there are roughly 1 billion neutrinos that go through your thumbnail every second. They're just streaming right through us all the time, continuously. And that would be a bad thing if they were interacting, but in fact, they have no charge, so they don't participate in the electromagnetic forces that Robert was talking about. They're extremely weakly interacting. In fact, they go right through the Earth by and large. And in general, if you had a hunk of lead about 9.5 billion kilometers long, which is big, a typical neutrino would travel through that without interacting. So these are wisps of near nothingness. And our job is to try and find and study this particle with essentially no mass, no charge, which just goes through everything without interacting. And we get a lot of money to do that. So why are people excited about this? Well, we learn about physics from the smallest scale, these neutrinos. I mean, we are fundamentally interested in the neutrino itself as a particle, but also it tells us a lot about physics on the grandest scales. So I talk here about what I call the bread and butter, which I learned yesterday was actually soup and underwear. But this is what we are actually trying to measure, but the implication, the icing, is learning about the structure and the evolution of the universe. So I'm going to try and tell you a few things about what we can learn about. It was mentioned by other speakers today that, in fact, neutrinos come from the sun. They come from the fusion reactions at the center of the sun. And this is a little pictogram of what our sun is doing. And at the very core, where all these fusion reactions are happening, the neutrinos are streaming out and coming to Earth. If we want to understand what's happening, what is making our sun shine, which then affects all the convection and all the other thermodynamics that affects the sun here, we don't know anything about that because we can't see inside. The light which is produced in these reactions actually takes 1 million years to bounce its way outside to the core, and so all information is lost. But the neutrinos come straight out. And this was actually the original motivation for studying neutrinos, was to study our sun, because we thought we knew everything about neutrinos. Supernovae are another thing that studying neutrinos tells us about. In fact, there was a famous supernova, 1987A, in which various detectors around the world, which were sensitive to neutrinos, saw the neutrinos. What's fascinating, the supernova is the death of a star, where all the matter, which is normally held out there by the radiation pressure pushing out from all this burning, when that fuel is gone, the whole thing collapses on itself, and it elastically explodes back out into outer space, and you get these great cataclysmic explosions. This is the stuff that when I talk to kids, this is what they love, seeing these movies of supernovas. And they really are substantial. But the trouble is, optically, the light comes out after the neutrinos. And so when you want to study how these are forming and you see the light, it's already too late. The interesting stuff has already happened. But because the neutrinos come out quicker, if you can catch these neutrinos, we're actually connected to a network of other experiments. And if we see a burst of neutrinos and they see a burst of neutrinos, and enough people see it, then people at NASA and the Hubble Space Telescope and all these people, they want to know because they're going to turn their telescopes around and they're going to start looking where we say these neutrinos are coming from and try and see if they can see the turn on of one of these supernovae. So that's one of the things we can do. And of course, neutrinos affect, because we now understand that they have some mass, they have been part of all this discussion of the future of the universe. Will the universe expand forever, or is it going to collapse again? Because they have mass and are gravitationally bound, they affect very much how galaxies and large structures form in the universe. And then there's this question, where is the missing dark matter and energy? And this was on a slide also that you saw earlier this morning, which wasn't explained. We don't talk about this. This is dark matter. If you weigh the universe, and we have ways of measuring the mass of the universe, we have ways of measuring the mass of galaxies, and we can tell how heavy a galaxy is. We can also count all the stars in a galaxy, and we can add them all up, and we can add up all the things we might expect to come from black holes and for these extra planets, neutron stars that don't produce light, and we can say, how well did we do? And in fact, we can account for 5% of the universe. There's 95% of the universe we have no idea what it is. And it's in the form of some dark matter that must be everywhere in our galaxy, affecting the rotation of the galaxy, but weakly interacting, as neutrinos, weakly interacting, so they essentially never interact, so they don't make their presence known in a visible way. And we have some clues on how we might actually search for this stuff. But I think it's an embarrassing fact to most of us that we don't really know what's out in our universe. This is a picture of Sudbury, which I like very much, so I had to find a way to put it in the slide. This is the northern lights over Sudbury. You can see this is the famous Inco smokestack, which is very much the heart of Sudbury as a mining community. All the acid rain from there rains down on our heads and has funny effects. But these, of course, as you probably know, the northern lights are produced by cosmic rays, which are coming from outer space, the plasma, which is coming from the sun and the solar wind and so on, striking our upper atmosphere, creating these ions, which are then collected up in these strong magnetic field lines of the Earth. And cosmic rays, in fact, although we don't particularly study them, in fact, the reason that we go deep underground is to get away from the cosmic rays. And I'll tell you a bit more about that in a sec. But in all these reactions that are happening in the upper atmosphere, we are producing neutrinos. And it's another minefield for us to be able to study these neutrinos. These are coming from cosmic rays which came within or even external to our galaxy. They have tremendous energies, millions and millions of times more energetic than the sun. So they're a different type of neutrino. We can learn different properties by studying these what we call atmospheric neutrinos. So let me just make a few general comments about both neutrino and cosmic ray experiments. This is a poor picture of a simulation of what one of these cosmic rays does. A particle comes into the upper atmosphere, collides with, say, an oxygen or a nitrogen, and produces, because it's got so much energy, in E equals mc squared, you can convert that energy into mass, and so you can produce all these particles that we know and love, but they only live for a very short amount of time, for the most part. And so in order to explore, these are difficult experiments, and this actually goes back 50 or 60 years or so. This is Victor Hess. He wanted to look at these particles that we believed might exist. And his only way of doing his experiment was to get in a balloon, and there's his family sending him off, and off he goes up 5,000 meters into the air with his detectors to try and look for these particles. They're tough experiments. To give you a feeling of some of the other neutrino experiments, this is the Amanda Neutrino Telescope. It's at the South Pole. Not the best place to do an experiment. It detracts on your family life, certainly. The detector itself is 2 kilometers under the ice, and it's about it's a kilometer and a half long, deep into the solar polar ice. You have to The idea there is that the ice is under such tremendous pressure that it's essentially a perfect ice. There's no cracks, there's no flaws. Neutrinos which come in and interact in that ice produce a little flash of light, and that light travels through the ice without stopping for large, large distances. And so you can actually drop detectors down into the ice. And it's quite easy to put a detector. It's expensive because of your location, but essentially you just heat water and you have a big heavy object and it just melts its way down. And you drop it down with strings 2 kilometers down. It's a really exciting project, but it's a difficult project. This is Sudbury, where we're doing the snow experiment. This is the entrance into the mine. This is the actual mine shaft where, in fact, you can see the wires that go up and our cage drops down, and we drop down 2 kilometers underground to our experiment. Again, not the easiest experiment to do. And as I mentioned, these cosmic rays, which are raining down on us all the time, and it's worse if you happen to be up in the plane, of course, you get much more radioactivity. We have to get away from those because these neutrinos are so hard to see. Even though we've built as big a detector as we can build, we're only going to see 1 neutrino an hour, say, on average. And yet the flux of other things raining down on us here is hundreds of thousands of particles per second we would be seeing in our detector. And to try and find that neutrino in all that other stuff which looks pretty similar would be impossible. So we go underground. This is what it looks like if you we're 2 kilometers down here. It's an active mine. Inco are still mining all this ore, taking it out. So our daily routine is to come down 2 kilometers on this elevator shaft, and then we have a couple kilometers to walk in to the snow site and tromping through the mud, and then at the end of that suddenly is our lab. This is what it would look like because, of course, it's very difficult to photograph being enclosed in rock. It's the size, to put a scale here, it's the size of a 10-story building from top to bottom. And the essential ingredient is this sphere here, which holds heavy water. The heavy water, it's just like normal light water, except as it turns out, the hydrogens, which would normally be H2O, have an additional little neutron on them. And that has special features which allow us to see neutrinos that nobody else has ever been able to see before. And that's the unique feature of this detector. I must say that it's what makes this detector uniquely Canadian. We were able to get our hands on 1,000 tons of heavy water on loan. To replace this would cost us $300 million. And we get it on loan from Atomic Energy Canada Limited because they use heavy water in the CANDU reactors. It's part of the Canadian reactor program. And so they have facilities which extract heavy water out of normal water. Heavy water is not radioactive. In fact, that would be incredibly bad for us because it would mimic all the neutrino signals. In order to see these tiny little flashes of light produced by the neutrinos, we have about 10,000 photomultipliers surrounding the detector. And it's akin to trying to measure a candle burning on the moon with the detectors on the surface. It's a very tiny flash of light. This is the detector while it was being constructed, just to give you a feeling of the size. Everything, of course, comes down in this tiny little cage to get down there. So we had literally millions of pieces that came down and were reassembled underground. And we had to actually go to the submarine industry to build this thing because they're the experts at building these high-pressure bubble submarines and know how to put this acrylic together in a way that won't pour your $300 million of heavy water out. So these are some more pictures of the detector. This is when it was essentially all finished and we were ready to start filling the thing with water, the fisheye lens. This is our purification plant. Radioactivity is a real issue at Snow, and we have to get all of the radioactivity out of the water. And so we spent years and years developing techniques, and we believe this is actually the center of our detector is the point of lowest radioactivity on the planet. This is the drift that we walked through to get in there, and in the interest of time, I will just very quickly mention, in order to make this, it was thousands of years of scientist years, hundreds of scientists we have on the project over the years, and it's been an exercise from conception to real results of about 20 years. This is what an event looks like. At the bottom is the electron coming here. It makes a little flash of light. And these are imaged which of the photomultipliers the little light sensors actually saw. The neutrino, and you can see it forms a nice ring as it ought to, and so on. So what have we learned? Well, first of all, neutrinos are changing from one type to another between the Earth and the Sun. That's the fundamental thing. And what I say here is imagine that you have an apple tree, and when the apple falls off the tree, when it lands on the ground, it's a banana. That's basically, in a nutshell, what we've proved has happened with neutrinos. And this has been the problem for 30 years, that neutrinos coming out of the sun were not at the rate they were expected to be. And so now this puzzle has been solved. We understand that they're changing from one type to another. The big surprise is, well, why this has impact is that neutrinos must have a finite mass. It also showed that, in fact, what we understand about the sun was correct. Our model of the sun is accurate. And, well, the mass of the neutrinos, unfortunately, is not enough to contain us gravitationally to pull the whole thing back together to cause this big crunch. Neutrino masses are also insufficient to account for all the dark matter. Now, I've run out of time, so I'm going to skip a couple slides here in the interest of time. This was the response from the scientific community. Or as mentioned, we were the #2 breakthrough in a number of magazines and editors over the years. I wanted to mention John Bacall. This is a guy who for 30 years has been saying, this is the model of the sun. This is how many neutrinos are coming out. And the experiments have been telling him for 30 years he's wrong. And yet he stuck to his guns. And now our experiment has actually proved he was right. And I had a chance to talk to him shortly after our results. And he said he was dancing around his living room. He was so excited. For hours, he just couldn't stop. And he was quoted in the New York Times as saying he felt vindicated. The DNA of an evidence is in now after 30 years. And of course, in 2002, we got the Nobel Prize. Not we, the Nobel Prize was issued for contributions to detecting neutrinos. And so it's been a great year for astroparticle physics. And now I'll just finish off with my last slide of where do we go next? Well, we have, of course, continue the SNOW program. We have lots more to do. There's a big physics program. It's rich. We're just touching on it. In the process, though, we've developed all of this expertise to do this kind of underground physics. We have a great technical staff. We have great scientists that have figured out how to make this work. And there's a lot of open questions. Where is the missing matter? What's the mass of these things? We know they have a mass, but we don't know how much it is, and so on. And this whole area of particle physics is just booming right now. There's more people coming into this field than any other field in physics. And it's a nice combination of particle physics, cosmology, and astronomy. And so what we have now is basically my last point is SNOWLab. This is our new idea. And SNOWLab is basically, it's actually now being funded. We have the money in our pocket. We got through the Canada Foundation for Innovation a grant to develop SNOW from a single experiment into a major international facility where people from all around the world are going to come to Sudbury and they're going to site their experiments there and they're going to look for dark matter. I'm also on a dark matter experiment and other experiments, and it's going to put Canada and Sudbury really on the map in this field. So thank you very much.
So tell me,